So today I want to talk about how can we use VR for science, and why do I want to talk about it? I started doing VR in 2005, and this is the very first virtual characters I've ever created of Christina. And fast forward 10 years later, 2016, this is a photogrammetry representation of myself. Ignore the hair, I didn't like that part. But anyway, so in the past 10, 20 years, VR really have changed a lot. Not only the ability we are able to create really realistic looking virtual characters, but we're also able to really animate them to a very sophisticated, with a very sophisticated way. In this case, she's animated with motion capture data. But then also on top of that, we're able to program those virtual characters to respond to words in a sort of realistic way as well. So basically what I'm trying to say here is that our ability to create realistic, expressive, and responsive virtual characters made it possible for us to have a meaningful social interaction in virtual reality. And that is what I have been doing in the past 13, 14 years. So I've been working on using VR for psychotherapy for social anxiety, and using virtual characters for medical doctor communication training. We've been working with antibiotics prescription, child abuse. I'm working on another project now as well I can't be talking about. And then I also work with neuroscientists looking at using characters to understand how people with autism react differently to social interaction, social situations. But the reason why I am here today talking about scientific VR is really to do with this experience I had in 2017 when I was in IEEE VR, which is the biggest VR international conference. It's been going on probably 20 years or so every year in the US, sometimes in the UK and Asia as well. And so I tried this VR application with HTC Vive, where I was in somebody else's brain scan data. And I really felt, because at the time I was just left my work from UCL neuroscience. So although I don't deal with brain scan data, but I see, seminars, I see fMRI data all the time. But this is the first time I was inside fMRI data and really changed the way I feel about the data. And not only that, not only I can see all the sort of data point around him, and I really feel inside someone's brain, but also I can grab a sort of slide, and I can move the slide. And as the slide moves, I can see different visualizations of color basically changes, and different color represents the direction of blood flow in the fMRI scan. And being able to do that, I really feel that I was really able to appreciate the complexity of the brain, the complexity of any problem that may occur in this space. And that's very useful for me because I work on medical doctor communication, how doctors talk to their patients. And a lot of the times, the problem is, doctors trying to explain really complicated medical problems to their patients, and they don't have much time, right? And you can't use pen and paper and some simple slides you display on the 2D screen. It's really not enough, right? But if they can actually explain the surgical procedure or just the tumor they have in your brain with displays like this, that might really change the way they communicate with each other. And this might also then further help scientists to communicate and understand problems this way. And then this might be able to use it to teach certain research areas, right? So that we can actually remember our experience in a space like that rather than some knowledge I have obtained by looking at something, right? So this is really why I really got interested in this area. But I just wanted to make sure, because I'm a researcher in VR, right? I just wanted to make sure you understand that this is not a new area at all, okay? And actually, there's a book called Visualization in Scientific Computing in 1987, which defines this area as an area to help scientists make discoveries by improving their perception of data. And actually, as early as 1967, Fred Brooks started a project in this area. And this is something, and virtual reality was actually born in 1965, if you don't know that. And the name was given in the 1980s by Gillies. But anyway, so this picture is actually from 1977, 10 years after this, is part of this project, but it's 10 years after the project started, which is the haptic display for scientific visualization. So basically this guy is trying to put these things together, and he has this device which not only tracks how he's doing it, but also gives haptic feedback of how these two things will interact with each other, right? And there's actually a paper Steve just mentioned, or the previous speaker just mentioned, that There are lots of things I want to run if VR actually helps for scientists to learn or manipulate data. And actually, there are lots of evidence, even in this project, they're looking at exactly that. So that might be a good place to start with. And yes, I wanted to really talk about, okay, so this actually happened in 1967 already. But why are we really looking at this problem again now? Why are we sitting in this room now? So in order to answer that question, I need to probably go back to what is VR, right? So lots of my students ask me, what is VR? What is the best definition? And I say VR is three things, okay? 3D models displayed with a 3D display on which you can interact with them in a 3D space with your hands, right? So in this case, we have the 3D model, this virtual character, and then my student put this, is looking at a character with Oculus Rift, and she's also interacting. She's actually driving this virtual character with her own body through a Kinect, okay? So this is an example of VR. These are the three elements for me how VR happens. And if you want to know more VR, we have a Coursera specialization on VR. You're more than welcome to check that out. So what is then scientific VR? So for me, scientific VR is obviously you start with 3D models, and for scientists in this room, I'm sure you have all your data actually 3D or 4D, even higher dimension than 3D. So what you need to do is just really to then plug your data and get it to display on a 3D display. This is not a hard problem. However, some people working in VR may be sweating now, because there are lots of technical things you have to get it right. But again, it is a solved problem. It takes iron tile to get it to work, but it's not that difficult. But I think the problem that is really yet for us to work out, the research problem here, is really clear: 3D interaction. Okay? But again, this is not a new problem. I mean, okay, this is a problem because in computing we're very much used to interacting with a machine with keyboard and mouse, as Steve just said. But actually, we're more familiar with 3D interaction because we interact in a 3D world every day since the day we were born, right? But it's a matter of really understanding how we interact with the real world and how do we then put it in a computer, which Marco will talk more about. But I just want to add one thing. I think the whole thing might be actually coming back to how I sort of started, because I started looking at VR from sort of a social perspective. I'm interested in social interaction in VR, but I don't think scientific VR is not social. And actually, as Esther just said in the beginning, she gave this example about how cancer cells actually interact with each other and how some cells are like police in the society, some cells are like friends, right? And that is actually a really good way probably to look at those data to actually help kids to learn, or even PhD students to understand data. So I think for me it will be very interesting to see if we can actually apply sort of social interaction in this space as well. So on that note, I'll pass it to my colleague Marco Gillies, who will talk to you more about 3D interaction.
Hello, I'm Marco. I'm also at Goldsmiths, University of London. I realised that I've put absolutely nothing about myself or my research on my slides, so I better introduce myself briefly. I'm also a VR researcher. I've worked for many years with Sylvia on a lot of the similar social VR problems. Today, I'm not really going to talk about that so much. I'm going to talk about, as Sylvia said, VR interaction, which is something I've also worked on, but I want to give an overview of how this relates to how it might relate to scientific virtual reality. So the most obvious thing when you look at VR is that you've got two screens and a headset, and you can think about the visual side of it, and that's really important. You can see things in 3D. But I'm going to argue a bit today that really the biggest benefits come from interaction, and I'm going to give you a little bit of an overview of what that might be. Now, what I see as the most important benefit of virtual reality is that it reproduces real-world sensory motor contingencies. Now, what's the sensory motor contingency? This is a model by Noe and O'Regan of perception, which really views perception as the interaction of our movements and our sensory data. So the nature of how we perceive the world as 3D, and they'll even talk about consciousness, is down to not simply the sensory data coming in, but its relationships to our movements. And we don't really get that in the same way on a screen, but in VR, the minute you put on a headset, it's tracking your movements in 3D. And it does something extremely simple but extremely powerful. As you turn your head, what you see changes, and that's something that we, that's innately part of what it is to be human and what it is to be in the world. But because VR reproduces that, that causes us to feel as if we are in a different space. We don't get that with a screen, even a very large screen like this. And that means we don't feel we are inside the world of this screen in the way that we are in virtual reality. So it is that close interaction between our movements and our perceptions that creates the virtual reality experience. And that's straightforward for viewing and for the headsets, but I think there's also a lot of power in the use of our hands and as a means of interaction. So, I'll just put this slide up of sort of, you can hold a mug in VR and move it around, and in some way reproduces the experience of holding it in, a real mug. I mean, there's stuff that it doesn't reproduce because this is a game and it doesn't have proper hand tracking, so it's not totally like that experience. But a lot of the benefits are that you have this experience, which is very similar to interacting with physical objects in the real world. I can throw this at people. That wasn't what I intended to do. So I can pick this up, I can turn it around, and I can look at it in different ways, and I can really understand this quite simple object in this way, in a better way than I was if I was simply looking at it on the screen. And the idea for today is that this can transfer over to very different kinds of objects that I can't do that to in the macro scale we live in. So we have, I'm not a biologist. I will say some stupid things about the biology. I'll leave it to you to interpret what that is. It's coming from shot from Seath at Synth. But the idea is we have these micro scale structures that we can interact with in the way that we interact with real objects. And part of that is viewing it. So we can kind of go and look at something closely, we can look around it, that can help, we can pick it up and turn it around, these very natural interactions which can help us interpret these kind of 3D data. And then possibly there are new things there are new contingencies, because these structures don't necessarily work in the way that macro scale objects work. And I think there's a power to looking at how do we interact with these objects that reflects their behaviour that is maybe slightly weird to us, people who live at a human scale. And so we not only interact with, say, molecules with kind of real world sort of macro scale contingencies, but do we need to actually create new sensory motor contingencies? And because this is the edge of my understanding of the biology, I can't really go much further than that. That's kind of an open question to you, but can we represent, say, the forces or the various interactions between our atoms in some way that is not simply visual, not simply video, but Steve was talking about sort of all the interaction you can create by simulating the physics. How can we interact with that and learn an intuition of how these things behave? So these sensory motor contingencies, they're what give us the intuition about what happens in the real world, what happens if I drop something. Can we use this interaction as a way of learning better intuitions of scientific data, which I'm sure you all know is very hard. I'm going to briefly give an overview of some of the various sort of things we can think about in terms of interaction, various forms of interaction. How much time? I'll try and be very quick. So we can have quite abstract interactions. That's what I would normally call, a standard computer sort of phone type interaction. You have a user interface. Very important, very useful. You need that, but it's not going to sort of have these kind of sensory motor contingencies. You can have natural interaction, which is very much modeled in the real world. I pick something up, I move it around, and I think that's going to be key to creating, really understanding things. But also, you can have something that, this is a phrase by Doug Bowman, a very important 3D interaction researcher, called magical interaction, that you can have ways of interacting that are not sort of clicking menus. They create their own sensory motor contingencies, but they're not they don't exist in the real world. And this is an example of a game that's become very popular called Superhot. And one of the key features is that time changes based on your movements. If you're still, time doesn't move forward. If you're moving, time moves forward. And because that's a very direct mapping, I do feel it creates a new and quite interesting sensory motor contingency for me, the relationship between my movements and time. And that, I feel, is an example of how we could create new ways of interacting with data that sort of reflect it. I mean, I'm not necessarily saying we need to slow down time with our movements, but I can talk in much depth about it, but I think there's a very tight loop of movement to time to vision that really creates a sense of something very learnable. Anyway, I'll talk about another couple of modes. There's another kind of distinction. One is that a lot of interaction in VR is just directly mapping your movements into the virtual world. So this is a game where you slash things with lightsabers, and it's kind of fun. But it's basically just my movements are tracked and it's mapped into the real world, and that's quite simple. So that's quite a simple sort of thing to implement. On top of that, you can implement what I call object-focused interaction. That's really about, your movements are directly mapped, but the interesting things happen with the objects, and this is an example. I imagine a lot of the work we'll be talking about here is this. You want a really complex, model of that molecule. But there are also, the other thing we can think of is what I call movement-focused interaction. So this is very much like traditional interaction design. You're designing an object, you're designing a thing that you can interact with, and the interactions are quite simple. But there are also gestures. This is one example I've had of my work, which is I was working with some archaeologists on movements and gestures to explore an archaeological site. And I won't go into some of the details, but they had sort of gestures which were reminiscent of digging work in order to, they were quite abstract, but they were reminiscent of their previous work. And the focus there was, we weren't looking at designing a thing to interact with, we were thinking about the people's movements themselves, and that rather changes how we do interaction design. And it brings in something called interactive machine learning. If people are interested in machine learning, ask me about that later. It's a very interesting thing. Two last things I want to bring up. One technology that I think will be very important I haven't worked on is haptics. So at the moment, the ability to feel touch in VR is very limited. I think in the future that's going to be more important, and I think there are some really good haptic devices that can be integrated so that you can actually feel things, and with the kind of setups we can have here in scientific VR, I think this will be very important. And also coming back to Sylvia's last point, sorry for the cheesy stock photo, but science is a collaborative endeavour, and that has a number of features. Firstly, VR can be a great collaborative platform, because even if you're across the world, unlike a Skype call, you are all in the same space, and that means that body language works. So you can look at someone, eye contact works, and particularly body language works when you have a focus interaction. You have an object you're interacting with. I'm interacting with this, I'm talking to you, I'm talking to you. These kind of complex sort of uses of just our gaze, our eyes, which could be very difficult over Skype, can work in VR. But it also changes the nature of the interaction with the objects themselves, because it's no longer, if it's a one-person thing, what matters is what I'm doing to the object. It's between me and the object. But the minute that it's a multi-purpose person thing, whatever I do to the object could be just an act on the object, but it could be a communicative act. So I could, if I'm just using this, if I'm just writing myself, this is nothing. If I'm picking this up and showing it to you, it's a communicative act. So I think that's another important thing that hopefully we can explore today. So that's me. Thank you very much.